Yeah, we can't put any more people in this.
No, I don't think so. Okay,
Yes, great.
good.
Well, good morning, everyone. I'm really happy. It's a distinct honor and privilege really to welcome you to Cailin's master's defense here. As many of you know, Cailin comes from downstate Michigan, Detroit area. She came up here 6 years ago now to do her bachelor's in environmental engineering. Did quite well in courses, as many students do, but found courses weren't the whole of education. So she was also actively involved in Green Campus Enterprise. She got a CERT fellowship along the way to do research one summer looking at the effects of climate change on lakes. And so in her senior year, we started exploring opportunities to do a research master. Yes. And we had just received this grant from the state to do additional work on Torch Lake. And it's a curious project for a master's student because there were three distinct foci, three distinct directions that Cailin had to go in. First, she had to work with the local citizens committee, the PAC, assisting them with outreach to the public. So I'll let her tell you what she did on that. But in addition to that, a large report had been written about 10 years ago as to what was the history of Torch Lake. But that report stimulated a lot of additional remedial work, which has never been summarized anywhere. So Cailin was tasked with bringing that summary of the history up to date as well. And then the experimental, the science part of it was to measure PCBs in the water of Torch Lake to answer the question, has all this remedial work succeeded? Can we see any evidence that concentrations are going down? And then secondarily, because there are some big remediation projects planned for the next 2-3 years in a row here, to establish a baseline of concentrations against which we could benchmark future progress. So that's the work that Cailin has done. You know, in order to do that, she had to work with one of the most complicated instruments on campus, a GCMS, which is not a trivial thing for a master's student to learn, but she dove right in. Unfortunately, this instrument has a history of being extremely temperamental and not working for long periods of time. And so for the first year that she was working, she wasn't able to experimentally test out her methods, test the design of her samplers, and be sure they were working. So instead, she had to do a much more robust modeling effort than we had planned originally to, as conservatively as possible, ensure that we were going to get good results from this project. So blindly that first year, we set our samplers out in the lake and tested whether her modeling effort was worked out or not. And again, I'll let her give you the results on that. It wasn't until the second year that we really were able to get the GCMS running. And so for the past 6 months, we've been kind of deluged with results, and you'll see the outcome of all of that today in the final verdict. So I don't want to steal any more of Cailin's thunder or time, so let me turn it over to you, Cailin.
All right, thank you. Yeah, thanks for everyone showing up and being here today. It's really great to see so many faces. So really, yeah, I'm just going to dive right in. What we did was work on applying passive sampling to explore remedial progress in our local Torch Lake area of concern. And we also dived in a little bit to interlake variability of PCBs, but that is really my third chapter, so we're not going to focus on that necessarily today. But if you want to, when the thesis is published, go ahead and read it. The first chapter is mostly based on an introductory chapter, so it's really a broad overview of all of the environmental policies and programs that have been in place at Torch Lake, as well as a summary of the more recent remedial progress that has been made in the lake, and that's what we'll be reviewing today. And then the second chapter is our methodology on the use of passive samplers for applying a baseline of PCBs in Torch Lake as of 2025. And then we also work through a comparison of our study to the last time passive samplers were applied in Torch Lake, which was 20 years ago, back in 2005. So again, the focus of this talk is Torch Lake, and many of you are locals, of course, but if you're not familiar with where Torch Lake is, it is located in Houghton County, and it, along with Michigan Tech and the other study lakes that we've looked at, are located within the homelands of the Keweenaw Bay Indian community and the territory established under the Treaty of 1842. Torch Lake is also one of 33 active area of concerns remaining in the Great Lakes Basin, of which there were 43 total designated in the 1980s. And that's really to say that less than a quarter of area of concerns have been delisted in the past 4 years, really to draw attention to the fact that remedial progress is slow. And that's, of course, not to diminish any of the work that the communities and agencies have been putting in. It's really just to draw attention to the fact that, again, remediation is slow and there may be some things that we can do to improve that work. And so this study really focuses on polychlorinated biphenyls, or PCBs, which are man-made organic chemicals that were manufactured between 1929 to 1979 when they were banned by TSCA, or the Toxic Substances Control Act. There were and are 209 individual congeners present from this family of chemicals. So if you're not familiar with what PCBs look like and how they're structured, this is a biphenyl molecule, and what happens is on each of these hydrogen atoms on the outside of the molecule, those can be replaced with a chlorine atom, and so both the number and arrangement of chlorines on that molecule will make up the family of 209 congeners. During their production phase, the primary uses were in oils, so they were produced as aerochlors, which are mixtures of PCBs, but they were used as oils in transformers, capacitors, other electrical equipment that required high capacity fluids. And so as of today, they're mainly a byproduct and released through inadvertent releases of pigment and dye manufacturing, waste incineration, others. So their chemical structure is unique and makes them bioaccumulative and lipophilic in the environment. So what we're showing here is an aquatic system. And what happens is that the PCBs can then be absorbed into organism skin and then uptaken and increase in concentration. So that's termed as biomagnification up through the food web, in which case the highest trophic level organisms are going to contain the highest concentration of PCBs. And so us as humans, we do consume fish, which leads us to knowing that the primary human exposure pathway is through fish consumption, which of course leads to a variety of health effects on the humans. But PCBs also do undergo atmospheric transport, so they're not only localized to their uses or their local uses, but they also undergo global transportation as well. So then to give you just a brief background on the mining and remedial action that has taken place at Torch Lake, it really starts with why Torch Lake itself was so unique and desirable for copper mining production. And that becomes a direct result of a substantial amount of native copper deposits being put in place over or being established, I guess, over the Keweenaw Fault. And Torch Lake also being so located near this fault, but also is a source of production. So a lot of the copper mining processes, they require water for that usage. And so of course, Torch Lake and Portage Lake and Lake Superior were those areas that were desirable for that reason. And so kind of to reach back into Torch Lake, in 1862, that was when the first stamp mill was built on Torch Lake, and that was over in Lake Linden, so the northern portion of the lake. Then in 1890s, with the implementation of the Rivers and Harbors Act, Torch Lake became exempt from dumping and harbor line rules, which essentially allowed them to fill in 50% of the lake's original volume with stamp sand. So that's over 200 million tons being put in place in the lake. Also in the 1930s, that's when the electrification of the mining process occurred, and that's when PCBs were first introduced into the lake system. And so what this map is showing here is the historical industrial buildings that were established along the western shoreline, and each of these buildings had used PCBs in their facilities, which is of course why Torch Lake is now known to have upland and within lake PCB sources present. So what is being shown here is burning of copper scrap at the Hubble processing area, the smelter yard at the Hubble processing area. And what was included in that was copper wiring, and copper wiring had included PCB-laden oils within it. And so that was later identified as an upland source area of PCBs to the lake. There are also hundreds of barrels at the bottom of the lake, or drums. That's what some people call them, but barrels, drums, they're at the bottom of the lake, and they have been suspected or also measured as containing PCBs within those barrels, or what remains of them. In 1968, so there was over 100 years worth of mining and reclamation activities taking place at the lake. So there's over 100 years worth of mining and reclamation waste at the lake as well. So that was in 1968 is when all of that action finally ceased. And then in 1979, again, that's when PCB manufacturing was finally banned under TSCA. And then in 1983, that was when the first fish consumption advisory was imposed on Torch Lake, and that was on sauger and walleye due to presence of fish tumors, which you can see from that little clipping there. And 2 years later, that was when the International Joint Commission designated Torch Lake as an area of concern site. And in relation to that designation, there are 3 beneficial use impairments. The first one being fish tumors, which was later removed back in 2007. And then there are 2 others that still persist today. The second one is degradation of benthos, which is the bottom dwelling organisms that make up the base of the food web. And then third is the restrictions on fish consumption. Now, in a year later, that EPA listed Torch Lake also on the Superfund site list, or on the national priorities list under Superfund, which also designates the site as a Superfund site as well. Then a year later, that's when remedial action finally starts to begin, and 2 additional advisories had replaced, fish consumption advisories had to replace the fish tumors advisory. So we had in 1993, it was set for mercury, and then in 1999, followed it up with PCBs. And so a lot of the work being done on the lake is under the purview of 2 different programs. The Area of Concern program, which focuses on the beneficial use impairments and targeting those, but the major limitation to that work in the very beginning, and of course why the beneficial use impairments are still in place today, was majorly a limitation due to funding, in which case the implementation of the Great Lakes Legacy Act and the Great Lakes Restoration Initiative, which are these 2 systems here, targeted that funding issue and eventually allowed them to go into the lake. This was a picture from the 2024 drum pilot study, which was done in collaboration between the US EPA and the successor landowner, Honeywell International Inc. So they have a formal agreement that allows them to cost share the expenses of a remedial action like this. And so what they were doing was going in and removing contaminated sediments, as well as some of the contaminated drums on the bottom along that Hubble processing area. And then they also have plans to go into the Lake Linden recreational area this summer and do some dredging and backfill of the contaminated sediments there. Under the GLRI, or the Great Lakes Restoration Initiative, Eagle and Manic Smith, we're going in and doing some test plots for capping, so where they go in and do some sediment coverage of the lake bottom and also constructed wetlands, because what they wanted to do was seeing that to see if benthic communities could be restored or brought back to a level that showed good signs that the lake was improving. And so what they had found was with the constructed wetlands that there was an increase in organism abundance and diversity. And then in the capping test plots, they had found also an increase in organism abundance. Under the Superfund site, their main priority was a focus on stamp sands, and that was mostly in part due to the risk of dust inhalation from windblown stamp sands. And so, of course, because there was a large and vast amount of these stamp sands across the area, they had broken the stamp sand piles and areas into 3 different operable units, so OUs. And the first one is the shoreline stamp sands along Torch Lake. The second operable unit is the submerged stamp sands, as well as the surface waters and the groundwaters there. And the third is selected areas around the sites, including other stamp sand locations. And so they ended up delisting operable unit 2, which is again surface waters, groundwaters, back in 2002, and that was mostly in part due to it was just not feasible to go in and cover the entire lake bottom with sediments. So they couldn't really do that. But the idea is that maintenance and cover of operable units 1 and 3 are going to benefit the recovery of OU2. So then the question comes down to what could be done about the metals, asbestos, other mining waste that was left along the Torch Lake shoreline, along other areas along the shorelines that were not addressed under the area of concern and Superfund programs, in which case that really became a target of the abandoned mining waste project, along with some supplemental work with the EPA emergency response branch, in which case they were starting in Lake Linden and working their way down the Portage Lake Lift Bridge to address all of those wacky wastes that were showing up still, or that hadn't been addressed under these 2 programs specifically. So, and then if we were to go in and categorize these remedial actions into decades, really a whole lot of work didn't start to really occur until the 2000s, when stamp sands when funding became available for the Superfund site and stamp sands could be covered, and that was addressing the human health issue of the dust inhalation. But there also was more influential studies in looking at where PCBs were being sourced in from the lake, either within the lake or upland sources. But that came, and what we're doing here is with the GLEC study, so that's the Great Lakes Environmental Center. That was done back in 2005 using passive samplers, and so that was one of the main studies that came as a result of the 2000s work. But in 2010s to present day, a lot of the work has been focused on addressing, again, the upland and within lake sources of PCBs, mostly in a movement to see that the lake is fully remediated and see that it gets recovered. And so we can address the BUI removal and eventually see an area of concern designation. We can see that delisted. And that's mainly a result of the community driven push for that work to get done. But of course, there are still a lot of persisting concerns involved at the lake. So in our work with the community, we did hear a lot about, whether or not it's safe to swim. That's always kind of a constant question revolving around the lake. And so it is safe to swim, but the main concern there is whether or not they don't want you, of course, to be ingesting contaminated water or contaminated sediments, which, sometimes can happen when you're swimming. So I guess there's a connection there. But in general, if you're swimming, it's not going to be an issue. The other concern, of course, is whether or not fish are safe to eat within the lake. And so, of course, there are still fish consumption advisories put in place, and that is another issue there. Which is inevitably why our project purpose is to go in and categorize or characterize PCB concentrations within the Torch Lake waters to assess the ongoing contamination that is present in the lake. And our project goals involve, again, providing a comparison to the last time passive sampling was done in the lake, which was done in 2005, and then be able to evaluate the effect the cumulative effect of 20 years of remediation efforts that have been taking place in the lake. And then along with those efforts, we also want to develop a 2025 baseline as a reference for future remediation efforts that are planned for the lake. And so you might be wondering as to why we're not looking at fish, since they're the primary human exposure pathway. So in the past 30 years, the state has monitored and continues to monitor every 5 years fish PCB concentrations. And so what's being shown here is a lipid normalized PCB concentration plot for walleye in Torch Lake, measured from Michigan Department of Health and Human Services and Michigan Tech over time. And the idea here is that walleye have shown no decreasing trend over time. All the while, of course, remediation efforts have been taking place in the past 40 years. So that's likely due in part to the fact that Torch Lake possesses an older fish population. So there is more of an unhealthy age structure in comparison to what we see from other lakes. But what we're what we do see is a greater abundance of older and larger fish in the lake in comparison to the younger fish. And so the older fish are going to be already contaminated with PCBs from their time exposed to PCBs within the lake. And so they're not necessarily going to indicate whether or not remediation efforts have made an impact on their contamination. And which is exactly why we go into looking at PCBs in the water column. And what we do is we use our LDPE, or low density polyethylene samplers, and we throw them into the water column and we leave them there for weeks to months at a time. And then we use something called the performance reference compound, or PRC approach, to be able to define our equilibrium concentrations. And so the way this works is we are starting off with a baseline of our known amount of PRCs and the understanding of how, and when we do place our passive samplers out into the water column, they're going to experience some loss of PRCs. And so from that loss rate, we have a good understanding of how analytes are uptaken in that same sense. And that might not make as much sense to you now, and I'm hoping that it will in just a moment. But in terms of how we go about selecting our performance reference compounds, we want them to behave similarly to our analytes of interest. So of course, we're looking to get PCBs. So we need them to have a same or similar octanol water partition coefficient, something termed as a KOW. And that KOW value is really a measure of a compound's hydrophobicity, so the tendency to leave water, really. And that's also often connected to its molecular size as well. The second thing is that we also don't want them to already be present in the environment. So we want them to, if anything was present in the water, the fish, or the air, then we excluded them from our selection list. We also don't want them to be present in any air chlors, which again are the PCB mixtures that were manufactured. And again, we want them to provide a range of those KOW values, in which case the larger and heavier compounds are going to have slower uptake rates, in which case they would require longer deployment times. And so we wanted to really be able to kind of understand how our PRCs were interacting with our sampler. And we'll get into that a little bit more in just a moment. But what we did was we selected 5 performance reference compounds ranging from 3 chlorines up to 7 chlorines. And so what our laboratory methodology looks like is we follow the works of Boai et al. And this looks a little bit complicated right now, and I'm not expecting you to completely understand what's all of the steps here, but if you do have questions, you can always ask at the end and I can clarify something. But so what we start off with is a sample preparation phase, in which case we're taking the LDPE strip from the manufacturer and pre-cleaning it. So we have it pure and removed of compounds before we start our performance reference compound spiking. And that step is done with an 80-20 methanol water mix. Then we subject our LDPE to one of 3 different uses. It's either going to be used as a deployment sampler, or we use it as a field blank or lab blank, and that's done to test contamination in the field or the lab. And then when we go back and we retrieve our deployed sampler, we remove any of the biofilm that had been present on the LDPE. Then we go into an sample extraction phase where we put the LDPE into hexane, and that's spiked with circuit standards. And the reason we do that is so that we can track our compound recovery throughout the environmental or the experimental process. That is then concentrated into a tiny little volume so that we can put it over silica gel, and that's done so that we can remove any organic matter or dissolved organic matter from our sample. We then concentrate it down a second time and then add internal standards, and that is what allows us to have a reference point for our instrumental analysis, which is again done with a really complex instrument called the GCMS-MS, or a gas chromatography mass spectroscopy mass spec, but for short we like, of course, GCMS-MS. And so we get something as an output that looks like this, and these are termed as chromatograms. So what we're expecting to see is something like our standard or our field blank, which they both have 14 compounds. Of course, we're looking at our 5 reference compounds, our 5 internal standards, 4 circuit standards. But then what we come to find is our deployed sampler, which eventually would hopefully have, of course, something where we find more peaks being established there. And that eventually leads us to our estimation of lake water concentrations. And so again, what we're thinking is that we need our baseline PRC mass, so we have a known starting point, and from that starting point, we're able to track that loss and be able to essentially say that loss rate is equivalent to the uptake of the PCBs from the environment into our sampler. And the idea is that if we had 100% loss of PRCs, that would be complete equilibrium because there are not PRCs in the environment. But we're never going to reach equilibrium with our sampler anyways, so that's just a side note there. So how we go about estimating like water concentrations, we first have to get an understanding of, again, our starting mass on our PRC. So we do some experimental batches where we determine partition coefficients between our sampler and the methanol water mix. And then that's allowing us to define what our masses are when we start. And when we finally go to deploy and then we retrieve them from the environment, we're again tracking that loss of reference compounds. So what you see here is a 20% loss of PRCs. That would say that we're at 20% equilibrium. Again, if we had 100% loss, it would be 100% equilibrium. And what we get is an LDP extract concentration. So that's not really representative of the water concentration or the concentration in the water. So what we have to do from there is we take in a partition coefficient from the water in our LDPE, and we use that to get a lake water concentration. We also go through a step of temperature correcting to the temperatures that were experienced while the sampler was deployed. And then further, we get it up to an equilibrium concentration. So we're applying that percent equilibrium achieved by our reference compounds to the same congeners that have the same number of chlorines. So for example, our PCB 36 is our reference compounds that had the compound that has 3 chlorines. And so that would be applied to all other congeners that have 3 chlorines. And of course, so what we want to do is then be able to validate our methods and make sure that things are looking as they should. And so what we do see from here, which is a plot of our measured partition coefficients. And in comparison, so what we're showing here is our measured partition coefficients in our green and orange and blue. It's not necessarily important which ones they are, but then we're comparing it to the black values here, which are Boai's paper. And what we see is that it does follow our expected thermodynamic relationship. We also have really comparable variability in our samples as what is observed by Boai. And the idea really is behind that is that we're not going to see the same partition coefficients between any 2 studies because everyone's using a different LDP from a different manufacturer, and there are a lot of different variables that contribute to some differences. So it's just a good indicator that what we're seeing is good here. Also, in terms of what we're expecting to see with the loss of our PRCs, the idea is that with increasing hydrophobicity, so that again, the tendency for compounds to want to stay out of the water, we would be experiencing a smaller loss of PRCs. In which case, when we were going in and looking and applying our mass balance model, we found that we were overestimating our PRC starting mass. And we also found that we were getting a larger loss of PRCs from our blanks. And so what we had found was that there was between batch variability that we needed to correct for. And when we were able to go back in and correct for that variability, we were then seeing a better fit of our measured data. We also, again, wanted to see and understand how our sampler was performing in terms of reaching equilibrium. And so what is being shown here is a timescale-based partition coefficient. It's not, this would be representing the time deployed, essentially. And what you eventually would find is that you come to equilibrium with the surrounding environment. And this is just for one congener being modeled. So we wanted to model what our PRCs would look like and compare that to our measured data, in which case those seem to correspond fairly well, which is a great thing. However, what we do notice is that, again, the heavier compounds are going to be achieving a smaller loss of PRCs, which is going to make it extremely hard to quantitate the uptake of the heavier PCBs from the environment. So what we're seeing here is that even with PCB 186, it would take 100 days to achieve 10%. So it makes it a little bit difficult for us in that sense. Excuse me. So really that's just to point out that this is a limitation to the passive sampling technique. If you're looking here, you see that PCB 8 would take 5 days to come to 95% equilibrium, and that is a 2-chlorine compound here. And then PCB 209 would take 28,000 days, which I don't think anyone here has time for, but that is 10 chlorine. So again, it's just, again, a limitation to passive sampling. And then lastly, for our validation methods, we were looking at comparing our temperature and time deployed. So these both look like what we're expecting to see. Over our extended time of deployment, we get a greater loss of our PRCs. And then as temperature decreases, we're experiencing a smaller loss of our PRCs there. And then to the fun part, sampling methods, it was a lot of fun, but we get to go in and deploy in Torch Lake 17 different times between August 2024 and October of 2025. And we were able to measure across 7 different sites at Torch Lake in all 4 seasons. And so what the sampler looks like going into the lake is something like the picture on the left, and then we leave it for about 1 to 2 months at a time, and then it comes back looking like something like the picture on the right. We also looked at measuring nearby lakes, so we were measuring at Portage, Worm, Gratiot, and Medora. And that's really to give us a good understanding of the background concentrations of PCBs in lakes, because all lakes are receiving atmospheric PCB inputs. And so we wanted to be able to provide a good comparison, again, back to Torch Lake, which has upland and within lake PCB sources. And so really what we're doing here is building on that previous work from the GLEC study, in which case they had found that Torch Lake was higher in concentration than their control lakes. And they're using a similar method. They're using an SPMD, so a semi-permeable membrane device. And the idea is that with atmospheric concentrations decreasing over time, we're expecting to see a smaller amount of PCBs in the control sites, especially. So we're expecting to see about a 70% decline in PCBs in surface waters. Not necessarily sure what we're going to see with Torch Lake, but that's exactly why we wanted to go in and measure them. And so of the 17 deployments that we had made, we had 12 successful. So we weren't able to recover 5 samplers, and that may have been a result of probably 2 different factors. One being that Torch Lake has really steep sloping sides. And so if you ever deployed right on the edge of that steep sloping side, it's likely that it could have just, due to wind or wave action, just got pulled below. Another thing is, and what we had a couple of different times, is that fishermen sometimes catch it on their fishing rod. And actually it's a really funny story, but the first time that happened was in Portage Lake. We had my next door neighbor actually had caught it on his fishing line. So that was a really fun experience, but yeah, it happened every now and again. And so moving a little bit more into what we were actually seeing from these results, is that we found that Torch Lake was not statistically different than control sites, but that's mostly in part due to the large variability between sites that we observed. And this is showing what we were able to detect specifically. So these are detectable chemical concentrations across our sites. And then in our seasonal variability, we also found that those were not significantly different. We were only able to have detectable concentrations measured in our summer samples. But we also look at something called our total PCB concentration, which is basically measuring, it's half our detection limit. And so it kind of gives us a representation of the number of congeners that have been detected by our sampler, in which case that somewhat is indicative of a seasonal trend being observed there. And then in comparison to comparing to the GLEC study results, what we're showing here on the right is a bar chart of the GLEC measurements in red, and they're referencing the left-hand axis, which is the 0 to 400 picograms per liter. And then on the right-hand axis is our measurements, which range from 0 to 20 picograms per liter. So that led us to saying that we observed a decrease of about 90% between our 20-year gap in studies, which is really great to hear. We also found that we had a domination by lighter congeners, which is typically more connected to atmospheric deposition, whereas the GLEC study had found heavier molecular weight congeners most dominant, which would be more indicative of localized inputs like the contaminated sediments and upland sources. So really the significance behind these findings is that we were seeing quite a drop about 90% of decrease between our 20-year study. In combination with the presence of lighter congeners being found most abundant, it is suggesting that remediation efforts have been successful in the lake and in reducing the PCB sources to the lake. It also could be suggesting that we see concentrations in fish begin to decline to levels not significantly different than control sites, which would be a movement towards removal of the fish consumption advisories, as well as a push towards the removal of the BUI associated with that fish consumption advisory. But again, we also always have to provide a cautious alternative, which would be to say that improvements might have to be made to our sampling methods so that we can improve our detection limits and have more congeners detected with more confidence. And so onto some of the lessons learned and what we could say about future work. Really, there has been a lot of study successes and, of course, a lot of failures in between, which has been a lot of fun to experience all of it. One of the main things, again, is to improve sampler design and be able to somehow increase our detectability. Field and lab experience, obviously, is always great. You really get to learn how to have fun in really intense environments sometimes. And let's see, continued limitations to remedial success. It's interesting to think that the Great Lakes Legacy Act requires 35% cost share from the potentially responsible parties. Not all area of concern sites do have potentially responsible parties or PRPs that are either willing to provide that cost share or are present at those area of concerns, which would just be another indicator that area of concern sites are not necessarily going to be moving forward, and so they might be left behind in remedial progress. And then it's interesting also to think about the abandoned mining waste project being unique to the Keweenaw. I always am kind of curious to see if that could be, expanded to other areas. That would be a nice thing to investigate. But then with work beyond passive sampling, I also got to work with the Torch Lake Pack and work on maintaining the website and going to outreach events and producing newsletters, which we have one being released tomorrow. So that's exciting. But really what it taught me is that it's really critical and important to maintain both accessible and transparent information to the public and keep the community engaged and just be able to, expand those outreach efforts and involve a lot of educational exchange between both the public, the communities, the scientists, and the agencies that are conducting the work. So really, I owe a lot of thanks to my committee, Dr. Noel Urban, Dr. Judith Berlinger, and Dr. Carol McLennan, along with my research group colleagues in and throughout the years. There's been a lot of you, and it's all been great. GCMS Instrumentation, Jimin, thank you. A lot of the MTU GLRC staff, of course, have been extremely helpful in a lot of this work, and the Torch Lake Pack, and funding and support from both the GLRI, MTU GLRC, and the Civil Environmental and Geospatial Engineering Department. And of course, thanks to people in place. It's been an awesome 6 years. So. Now, does anybody have any questions? Yeah.
You said that a lot of what seems to still be driving the concentration of high fish because of the older, the older walleye. Do you think that the fish will maybe start reflecting like younger fish start becoming more populated then that'll really start reflecting that the PCB concentration have.
Yeah, definitely. Yeah. So what they were showing in the DNR was, we could see an older fish population. And of course, those are again showing a higher concentration in their fishes. What we would expect then, hopefully, to see is that younger fish throughout the years, since all of these mutations have been, getting put in place, and that the sources have been being targeted, that those fish tissues would eventually show a lower concentration.
A related question about the tumors. Are the tumors caused by PCBs? And the second part of the question is what's the advisory that was lifted about tumors?
Okay, so that's a good question. So the original tumor designation did not have necessarily, they weren't necessarily sure where the tumors were coming from, but a lot of it was mainly associated with some of the chemicals that were being used in the processing of pepperwork. And so what they eventually disappeared over time. They were being tracked and measured by the PMR. But eventually they disappeared, and that was pretty much the reason why the fish tumors advisory was lifted, because they stopped appearing after maybe 10 or so years, I think. So, yeah.
I'm like curious how the like samplers work themselves. Like, are they made of like a colander first, and then like does it matter?
Yeah, great question. So the purpose of the colander is, let's see if I can actually show you a picture again. Let's see. Yeah, so the purpose of the colander really is to protect the sampler, because the sampler itself is the LDPE, so that little plastic medium. And what happens is we obviously don't want to lose it. We want to be able to, recover it from the environment. And so both, I guess the purpose of the colanders is to be able to contain it in some ways, and then also allow some flow of water, of course, through into the sampler. And then we also want to try and limit the amount of biofouling, because without it, we would probably have an increased amount of biofouling occurring on the LDP. And so that's another reason too, yeah.
And also, like, does it matter, do you think, where it sits in the water column? Like this,
Yeah, that's a good point. I personally, we did not really, we were aiming for mid depths here. It might end up resulting in changes if we were to go lower to the sediments, because the sediments are typically more highly concentrated in areas where they have been measured as highly concentrated. But we didn't look into it as far as that in this study. So no, sure. Yeah, Rob. Hmm.
Would that be something that needs to be
Mhm.
or something?
Yeah, definitely. It definitely, so biofouling would just be basically like another layer in between the interaction of our water and our sampler. But the idea is that with our use of PRCs, that's going to kind of help us in that way, because the loss is also going to be limited too. So. Yeah.
On the results chart that you showed, there might be some seasonality.
Mm-hmm.
So the orange is what's detected.
Yeah.
Can you?
Yeah. Like the difference between detected and total?
Yeah.
Okay, so detected is what we are able to measure above our limit of detection. So throughout our method process, that's what we're able to say confidently that we can measure. The total PCB concentration is where basically any congeners that were identified but below our detection limit are set to a value of 0.5, the detection limit, in which case they are able to they're able to represent the number of congeners that we were detecting, but not necessarily with confidence in that concentration itself. Yeah. Mm-hmm. Dr. Patterson, was that your question?
No, mine was more so, Cailin,
Yeah.
tremendous job.
Thank you.
An outstanding body of work for that.
Thank you.
Congratulate you on. Oh yeah, I've done these types of field. I've had to learn how to work with CMS.
Mhm. Yeah.
How was your experience working with from say
yeah.
perspectives of success, but possible challenges in communicating this message?
Okay, so that's a great question. I think I loved working with the pack. I think it was a great experience. I got exposed to a lot of different things that I wasn't really expecting to, I guess. Like, I mean, being able to work on a newsletter was kind of a source of creative outlet for me. So that was really unique and fun. And also getting to work with Carol and Dr. Urban really closely was a great experience. And also, I guess another thing is always being able to communicate science in an effective way, so that the community understands it, because I think that's the most important part. You want to be able to communicate the work that you're doing in a way that is most impactful and meaningful to them, and in a way that they understand, of course, too. So, yeah. Oh, yeah. Sorry. Let's see. Was there? Okay. Do I have to stop sharing? Let me see. Okay. Yes. Mom.
Hi. So I noticed on one of your graphs,
Yeah.
for your historical comparisons for the different areas, and you had Black Island listed.
Yeah.
So I noticed there wasn't a historical comparison for that one, for that location.
Yeah. So I'm gonna see if I can share this quickly. Here. Yeah, so I mean, they didn't, of course, measure at that location. So we were just trying to get to, I mean, similar points that they had measured so we could try and conduct a good comparison. So what we were focused on was again the Lake Linden area and this area over here, which they had found the highest concentrations to be. But we did monitor also at Black's Island as well, and that was kind of, I guess, mostly due to the bathymetry of the lake. So like the lake bottom was quite more shallow there, and so we were able to do that. But this site here was really difficult to do deployments at because it's about maybe like 40 feet up to like 10 feet really quickly, and Jamie got us out there and really helped us deploy that one. So thanks, Jamie. So yeah, we tried to conduct the sampling sites as close to as possible. Did you have anything else?
No, I was just curious about that.
Okay, great. Thanks.
I love you. I'm proud of you.
Thanks.
Well, it's not, let's think. Stop yourself to refreshments, otherwise the committee is gonna have to stay in public comments.
Thanks, guys. Love you. All right, guys, I think we're all leaving here, but thanks for being on.
Now I want to know.
You're so welcome, Cailin. You did awesome.
Thank you.
Proud of you.
You guys down because you're on max volume right now in this room. All right, okay. Thank you. It was great having you here. Seriously. Thank you.
Good job.